Hello, so what we're going to do today is go through basically the PowerPoint that I would have shown you if we were talking about this in class, about how to do the Exoplanet Lab, with an emphasis on first explaining to you what an exoplanet is, and then how you're going to do the analysis of the lab. So the first thing we're going to do is watch a video that is going to explain a little bit of this to us.
An exoplanet is a planet that orbits a star other than the Sun. In recent years, astronomers have discovered exoplanets as small as the Earth, but none of these Earth-sized planets have orbited stars close enough to study in detail. Now, a group of astrophysicists have discovered a new exoplanet that is Earth-sized and rocky, orbiting a star only 39 light-years from Earth, making it the closest Earth-sized exoplanet discovered to date. The researchers identified the new planet using an array of 40-centimeter wide robotic telescopes located in the mountains of Chile. The telescope array searches for planets by monitoring the brightness of nearby small stars, taking measurements of starlight every 25 minutes. If there is a
Watch
dip
the
in a star's
telescope
brightness,
closest
it
to us.
could indicate a planet passing in front. On May 10, 2015, one telescope picked up a faint dip in
It's
starlight
staring.
from JG 1132, a star located 39 light-years from Earth. To confirm this was indeed a planet, the telescope observing the star upped its observations from
And now
25-minute
it's done.
intervals to every 45 seconds. Coupled with observations from other large telescopes in the area, they found that JG 1132's brightness dimmed by 0.3% every 1.6 days, a clear signal that a planet was regularly passing in front of the star. Based on the amount of starlight the planet blocked and the radius of the star, the group calculated that the planet is about 1.2 times the size of Earth. From the planet's size and its proximity to its star, the scientists estimate the planet's average temperature to be around 450 degrees Fahrenheit. The planet is also likely tidally locked, meaning that it has a permanent day and night side, presenting the same face to its star, similar to how our moon faces the Earth. Although the surface temperature may be inhabitable compared to most rocky exoplanets that have been discovered, this planet is actually cool enough to have a substantial atmosphere. With more powerful telescopes, such as the James Webb Space Telescope launching in 2018, scientists may be able to uncover many more details about the planet's atmosphere, including the speed of its winds and the color of its sunsets.
Now, that James Webb telescope that they were showing you there, unfortunately, has been delayed so many times, it's getting kind of ridiculous. It is actually supposed to be launching in March of 2021 now, but unfortunately, given the current state of things in the world, that date might get pushed back again, and they have to launch it only at very specific dates and times because it actually has to be launched when things are in the right orientation. The telescope is enormous. It measures about 20 by 14 meters. It weighs over 6,500 kilograms. The main mirror that you saw in that video is 6.5 meters in diameter. Now, here's the really crazy thing. The price tag on this puppy, just shy of $10 billion. The idea is that it is truly a replacement of the Hubble Space Telescope and that it will make the images that the Hubble has done look like a joke, like it was a little teeny tiny telescope that you would buy at a toy store sort of thing. So let's kind of continue then. This definition then of an exoplanet, sometimes also known as an extrasolar planet, is any planet that is orbiting a star that is not our sun. So, for our sun, we've got 8 planets and Pluto orbiting around it and some asteroids and comets and things like that. But we know that other stars, the stars that you see in the night sky, they have their own planets also. And the big deal was always, how do we actually measure them? How do we know for sure that there are planets orbiting them? Over the past few years, we have seen ample evidence of these stars orbiting, so that the most current number that I've got for you there is that as of July 2019, over 4,000 confirmed planets have been observed orbiting other stars. So how do we do this? Well, clicking over to here, you see that Basically what we've been seeing primarily are not, and when I say seeing, we'll see in a moment how, but we've been mostly looking at planets that are big like Jupiter, the big giant gas giants. They're the easiest ones to see. But we want to find Earth-sized planets, and that's been really difficult up until now. The way to look for these stars, though, is difficult because if you point any sort of telescope at a star, it's like staring right into the main light of a lighthouse. All you're getting is this incredible glare from the star, and that's it. And what we're really truly looking for is like if there was a little teeny tiny firefly going somewhere nearby. So, how do you see that little thing in the big glare of the star that you're looking at? The main way that they've gotten to do this is something called the transit method. Now, you remember I said to you, watch that one telescope while things were, it was showing those telescopes kind of jumping around in that fast forward image. And then it was like one of them just stopped. That's because it saw something significant and it stared at it. Now, what it was doing was it was watching as the amount of light from a star suddenly dipped. It was lower light than it should have been. And what that means is a planet is going across the front of that star, like between us and the star. And when it does that, there is a noticeable dip in the light output of that star. So what they'll do is they'll collect data again and again and again, and by compiling it, they can make estimations of the size of the planet as well as its distance from the star. They also observe other things about the star, like it might have a little bit of a wobble from the tug of these planets, all sorts of things. Now, up until relatively recently, most of this data has come from something called the Kepler spacecraft, which was basically a space telescope launched, I think it was about 10 years ago now. It was about 2010, 2011, I think. And Kepler has been doing most of the data collection for us. Unfortunately, its main gyroscopes have been locking up over the years. And very recently, I think it was in late 2019, effectively Kepler locked up and couldn't collect data for us anymore. So it's not really on mission anymore. But what you're going to be doing in this lab is using real data, and you have to make sure that you pay attention to the instructions that I give in the lab for what group of data you're looking at, because you're not doing all four groups of data. This one that I'm showing you right here is group alpha, which is for the star 55 Cancri. That's its catalog name. But you might be doing a different group of data based on your last name. So please pay attention to that before you start analyzing anything. Now, you'll see that on the left-hand side, we list these exoplanets, and they always have very boring names. 55 Cancri B, C, D, E, F, and G. Those are planets orbiting 55 Cancri. You might say, where's 55 Cancri A? That's because at one point it was believed it might be an exoplanet, but then it was shown not to be. And once a name is used and then they verify, nope, that's not an exoplanet, it just gets tossed. It's never used again. So B, C, D, E, and F are verified planets orbiting 55 Cancri. And I've given you the period of their orbit in days and their mean, also meaning average, orbital radius in astronomical units. And remember, astronomical units is just a comparison to the size of Earth's orbit. Earth's orbit around the sun averages 1 AU, 1 astronomical unit. It's just a measurement of distance like any other measurement, so don't get hung up on it or anything like that. 55 Cancri G has an asterisk because we're not sure. That is one that they think might be a planet orbiting that star, but they're not sure. And we give you some data about it and say this is the period and orbital radius that it appears to have. But we want to verify. We want to know, is it possible that 55 Cancri G could also be an exoplanet around 55 Cancri? Now think about it for a second. 55 Cancri B, C, D, E, and F must all have approximately the same Kepler's constant value because they're all orbiting the same thing, 55 Cancri. So what we could do is use the verified planets, get their K constant, their Kepler constant value, and then compare it to the calculated value for Cancri G all on its own. And if the numbers are reasonably close, then we could say, yeah, Cancri G might be an exoplanet. But if the numbers are not reasonably close, then nope, they can't be. So what you're going to have to do is use a suitable averaging technique, that means you're graphing stuff, to take the values of the confirmed planets, graph them, and get a value for Kepler's constant. Think carefully about how you can do that with measurements of period and radius of orbit. How are you going to graph those after linearizing them in order to get a value for Kepler's constant? Then old fashioned, old school, you grab the formula K equals T squared over R cubed, and you stick in the values for your unconfirmed planet just to old school calculate the Kepler's constant. Then confirm, or I should say compare the confirmed and unconfirmed K values and see how close they are. Reasonable, could be a planet. Not close to each other at all, no, not going to be a planet. So, if you have any questions about this, especially if you're getting a little confused about how to do the linearization, think about it first and then come online and ask me some questions about it, and I'll try to help you.